I'm
You
ready.
did. Do you have your science packet?
No, I don't think I do have it.
Okay, I sent them on Jupiter the
I'm
other
gonna
day,
go check real quick.
but I'm also gonna put the stuff up on the screen for now, but you can check to get the files from Jupiter.
Okay.
Hey Leilani, did you get the science packet on Jupiter? I unmuted you.
My mouse is gonna be printing it for me when she comes home.
Okay, awesome. I'll put up the work that you guys need to see on the screen today.
Hmm?
I said I'll put up the work you need to see on the screen today if you don't have it printed.
Hello?
See you.
Is there no sound?
No, everyone's just on mute right now.
Okay.
Miss Vicky, sit up. Sit up.
Jalen, you're gonna need to find a way that we can see your face the whole time, okay? If that means putting a book and then you're leaning your phone against it, that's totally possible, okay?
Okay, everyone. It's 11:50, so I'm gonna get started. So we've got 40 minutes for science. During this 40 minutes, I'd like to see everyone sitting up in their seat. I want to see your faces. Please, don't get up and use the bathroom or go talk to mom, grandma, brother, sister, cousin, whoever that is. And we'll be giving you gentle reminders for what we expect. We know that this is new to all of us, but this may become the new normal for us. So we're just going to kind of grow into that. I'm going to go ahead and screen share the review. I sent out your packets yesterday because I know none of you got packets. It's okay if you don't have them printed yet. I'm going to screen share the review. So I'm going to do that now. Sharing, we need to share this. We need to share this. Give me a thumbs up if you see this review. Okay, take 3 minutes. Let's take 3 minutes and work on the review. Great. So I see Leilon just got started right away. I see Daniel's working on his review. Jessica, I see. Jalen, I see. Jason's finally using that mechanical pencil. Way to go. Mechanical pencils are like gold at Classical. Morris. 1 second. I'm trying to unmute you. Let me click it again. Go ahead.
Mr. Amador,
Yes.
what are you doing?
We're doing the review. As you can see, I've shared the screen. Every day we start class with a review. Same thing with remote learning. You've got about 1.5 minutes left.
If I might interrupt, Mr. Amador, can you hear me?
Absolutely.
We need everyone to sit up during class. Some of you are lying down, and I've asked you in private chat, so we all need to be seated up. Sit up, right? Because this is a professional environment, and that's what we need to look like. Jalen, let's sit up, please. Thank you, ladies and gentlemen.
Okay. So my timer for the review has just gone off. So what I'm going to do for the first 3 multiple choice questions, that is an error. It seems like we're supposed to have disabled that feature. So that maybe was someone accidentally drew that line, or maybe it was me. No, it wasn't me. Okay. So let's all start with our fists up. The number 1 will be A, 2 will be B. We all get how we're going to go from here. So let's start with fists up. We're going to do a review question 1 on the count of 3. Show your answer. Make sure that your fist can be seen in the video too. Some of you, so you got to actually look at, if you could see your own little video picture of yourself, make sure your fist is visible. All right, number 1, show your answers on 3, 2, 1, and go. 3, yes, it is called electromagnetism. The relationship between electricity and magnetism is called electromagnetism. 2, a coil of wire with a current is called a, fists up, just the fists, because we don't want to give away the answers to all our friends yet. A coil of wire with a current is called a, 3, 2, 1, it's a solenoid. A solenoid, so just the coil of wire with current flowing through it is a solenoid. Number 3, when a ferromagnetic material is placed within a solenoid, the resulting device is called an, our fists are up. We're going to show our answers in 3, 2, 1, and go. The answer is B, electromagnet. Take a solenoid. Solenoid is the coil of wire. Put a ferromagnetic core inside it. and then you got yourself an electromagnet. Why is an electromagnet considered to be a temporary magnet? Give me a hand. I see Chanel. I'm unmuting you.
Electromagnet considered a temporary magnet because they can lose their charge quickly.
Okay, so Chanel used the word charge. What word should we use instead of charge when we talk about magnets? If you want to correct yourself, Chanel, go ahead.
Energy.
Close, close, close. So charge refers to the electric force. I'm going to Tanzel. He's got a hand up. You're unmuted, Tanzel.
Taz, speak.
All right, we're going to go past Tanzel. We're having some technical difficulties. Can't hear Tanzel. Other hand. 2 hands were raised. I don't see those hands on my screen right now.
Jason was one. Jason, go ahead.
I've a question.
Yeah.
Remember that experiment that we did when we were rubbing magnets on the paper clips? Are those temporary magnets?
Are they temporary magnets? Yes, those are temporary magnets. So an electromagnet is considered temporary because it can lose its magnetism. So that's the word that we should use, not charge. Charge refers to like how much electric charge something has, like the electrons built up on it, if it has like positive charge or negative charge. Magnets have magnetism. A permanent magnet will keep its magnetism. A temporary magnet will lose it over time. An electromagnet is considered temporary because it only has magnetism when there's current flowing through it. Once you stop the current, it loses its magnetism. I'm gonna try to.
Daniel has a question.
You know, go ahead.
Oh, I was gonna answer number 4, but
Number 4, yeah, I kind of just went over that. Thank you. I'm gonna try to share a video with us all. You have to give me a thumbs up if you can hear the audio. If not, we will have to skip it. Give me thumbs up if you can hear audio. Give me thumbs down if you cannot hear audio. Okay. Well, you don't really need audio. You don't need audio. It's just music.
What's that?
So this device is called a galvanometer. What it does is it measures small amounts of current. So what we see in this video right now is that when we place a magnet inside a coil of wire, it's actually generating an electric current. So I'm going to pause the video there. I'm going to go to one of our scholars to just give a brief summary of what we just saw and what I just described was happening in that video. What do we think we saw in that video? I see some eyes are wide. I'm not sure what we just saw. This is what I'm hearing. I'm going to Carlo. Carlo, you're unmuted.
What? I can't hear you. I can
So
barely hear you.
Carlo, in the video, we saw a magnet that was placed inside a coil of wire. And when it was placed inside a coil of wire, what did we see moving on the screen? There was a device.
The Galvanometer.
Yeah, a
The
galvanometer.
little arrow.
So the key point here, Kaylin, the key point here is that we all need to remember, I'm muting you again, Carlo, is that if we put a magnetic field near a coil of wire, and if we change that magnetic field, maybe by spinning the magnet or by passing the magnet through the coil, it will actually generate a current. And we're going to learn today that this is actually how we generate pretty much, this is how we generate most of the power that we use as a society.
Jessica has a quick question.
Go ahead, Jessica.
Oh, I was gonna say, like about the video. Like, yeah, like in the video, it showed the galvanometer and how it works.
Yep.
It told us that it's to measure small amounts of charges.
Yeah, it used a galvanometer and how it works using small amounts of charges, and it showed that placing a magnet, moving a magnet through a coil of wire can actually generate a current. I'm going to share my, I'm going to screen share.
No.
Someone needs to get muted. Okay, there we go. I'm going to screen share a magnet that I have here. Do we all
Jalen,
see?
sit up.
We all see this magnet? Yes, I need it. Okay, so I just taken a regular bar magnet. I taped a paper clip on it so that I could actually hold it in place. The red side is the north pole of the magnet. That makes this the north pole of the magnet. Everybody think, what do you think is going to happen when I bring this north pole near the other north pole? We're all thinking, what is going to happen? Are they going to point your fingers together? Are they going to attract each other, or are they going to repel each other? Show me on your hands. Are they going to attract or repel? Yes, they are going to repel each other. So when I bring this near, it's actually going to cause this magnet to spin. And when the south pole gets close to the north pole, it actually attracts. Now, if I could somehow continuously change the pole that this magnet is facing, I could maybe get this other magnet to keep spinning around and around and around. Let's see if I can get the timing right. Let's see. Do you notice how the magnet in my left hand, which has the green paper clip, is now also spinning around? All right. How could we what I want everyone to do now is I want everyone to write, how could we possibly create motion using an electromagnet? So I just used motion with I just created motion with 2 bar magnets. What I did was I kept changing the direction that one of the magnet was pointing to the other, and it caused the other one to spin around in a circle. How could we use an electromagnet? How could we replace this second magnet with an electromagnet and get that to work? Everyone should be writing. Take 30 seconds. I want to see your pencils on the paper.
Tanzel has a question.
I think Tanzel's maybe looking to answer. I'll unmute you, Tanzel. Don't give your answer yet, but you can tell me if you have a question or if you're looking to answer. Where is Tanzel?
Also, if you guys have questions like, can I use the bathroom? Can I go get water or something like that? You can just put that in the chat so you don't waste your teacher's time.
Mr. Ramon, all right. Morris,
Yes.
go ahead. You have a hand up.
Okay, so what if you had like a bar magnet and then you like wrapped a solenoid around it? What would that do to the bar magnet?
What would it do to the bar magnet? So basically, you're just saying if you took a long thing of wire and you just like wrapped wire all around the bar magnet.
Yeah, and then like connect it to a battery.
Well, we know that a solenoid creates a magnetic field. So what happens to two magnetic fields? If you put one magnetic field within another magnetic field, do they interact in some way?
They align.
Yeah, they might align.
Yeah,
Carlo,
like
I don't know if anyone told a joke, so I'm not sure where your attention is. Yeah, they would align, but since you actually wrapped it around it, it might not move. If you wrap it tightly around the magnet, it might not do anything, but there could be some sort of an interaction like a force. There would be a push or a pull on the magnet and on the solenoid because they each have magnetic fields. So they're going to interact with each other.
Okay, thank you.
What about some ideas? So we've had some time to think and write. What are some ideas about using an electromagnet to generate motion? Now Tanzel's hand is up. Ms. Ramon, if you could find Tanzel. Oh, I found him. Got you. Go ahead. Tanzel, you're unmuted. Tanzel, go ahead and type your answer into the chat because we're not able to hear you. Let's go ahead let's get another answer while Tanzel's typing his answer into the chat. Your idea doesn't have to be correct, but we all have ideas. So what ideas do we have? I'm gonna call on Jessica. Jessica.
Yes.
How do you think we could potentially use an electromagnet to generate motion?
By changing the direction of the two electromagnets. Wait. Is that the electromagnet?
This is the electromagnet right here. I mean, right now it's not connected, but if I go ahead and connect it to my battery and I get current flowing through it, then yes, it will become an electromagnet. This is the one that we used yesterday.
I think Tanzel's written his question.
Can you, Ms. Ramon, let's see.
Yes.
For some reason, I'm not able to see the chat right now. Can you read what he said out loud?
And he said you could keep reversing the poles of the magnet.
Okay, so Tanzel says that maybe if we reverse the poles of this electromagnet, then we can get the same effect. I'm going to actually test that out now. What does it mean, reverse the poles, though? What does that mean to reverse the poles? Let's go to someone else. Chanel, I'm unmuting you. Go ahead.
What it means to reverse poles is like make it so the south pole like will attract to the south pole itself, like so the opposites do attract.
Well, opposites do attract anyway, right? North and south will attract.
I mean,
North and
for
north
the same
will repel.
For the same to attract.
Okay, that will actually never happen. South will always repel south, and north will always repel north. But that was a good idea. Yeah, if you could somehow make south attract south, then maybe that's a way to do it. How would changing the direction of current flowing through this electromagnet affect where the north and south pole are? That's what I want everyone to think about right now. And then I'm going to cold call someone. So if we have current flowing in this direction through this wire and then out this side here, that's one way that we could have current flowing in this way and out this side. But what if we had current flowing in the other direction and then coming out here? How would that affect the polarity, that means where the poles are, of this electromagnet? Jalen, you need to take a seat and turn around. Bailey, I'm gonna go to you. I'm curious what you're thinking.
I just came back. Like, what is this? Okay. Can you like repeat the question, please?
Okay,
Because-
Bailey,
Yes.
you should be like seated throughout the whole class, okay?
No, because I went to the bathroom. Yeah.
Okay. Well, we also just came back from an hour break, so. But Tanzel. I'm coming back to you, and I'm gonna see if I can get your audio. Go ahead and speak. Nope, still no audio from Tanzel. All right, Tanzel, type it in the chat. Everyone else is still thinking. So what if we have current flowing in this direction, comes in this side and out that side? Maybe that will make this the North Pole, and it will make this the South Pole. If we reverse the direction that the current is flowing, I'm going to give Tanzel like another few seconds to type it in chat, and then I'm going to share it out so that we can move on. And Ms. Rahman, if you happen to see anything come up in the chat, for some reason, I'm not seeing any chat messages right now. I don't know if anything, there we go. I've got some chat. I can see the chat. Okay, you could keep reversing the poles of the magnet. It would make South Pole north and the North Pole south. Yes, if you change the direction of the current that's flowing, you change the poles of the magnet. So I'm gonna try to do that right now. I'm gonna see if we can get that, if we can demonstrate that effect. So let me zoom this out a little bit so we can see a little bit better. I'm connecting my positive terminal, my positive side, to one end of the electromagnet and negative to the other end. So I should have current flowing through the electromagnet now. If I bring this close to the magnet, it actually does attract it. It does attract it. It's not so strong that it really gets it to fully spin around. But if it did get it to fully spin, then what I could do is switch the poles. Now, I'm not able to do this by hand fast enough. I can't like switch the cables back and forth really fast. So it's not practical like this. But the way that electric motors work, which we're going to read about shortly, is it very quickly, now I've just reversed the poles. You saw that I switched the sides that I was connecting the battery to the electromagnet. So go ahead, type in chat real quickly. What effect does that have? Changing the direction that the current is flowing through the magnet has what effect? I want everyone to chat it into the group chat. We changed the sides that we connected the battery to it, which changes the direction of the current. How does that affect the polarity of the magnet? Group chat. We've got Bailey. It says it switches the poles. It would reverse the poles. The effect is the pole switching. Yeah, so if the poles switch, we should expect then the opposite force to happen. Instead of a pull, we would expect a push. So before we were pulling, well, right now we're pulling on this north side because this is the south side of the, oh, you can't see this, can you? You need me to do that. Okay. So right now we're pulling, but if I were to reverse it, it will push. And I'm actually struggling to do this as a solo one person right now. But what we would get is if we could switch the polarity of this electromagnet, we would push away the north, and now it's pulling the south. Now, if we switch the poles, we could push away the south and pull in the north. Switch the pole again, push away the north and pull in the south. By switching the polarity of this electromagnet back and forth, back and forth, back and forth, back and forth, we can get this bar magnet to spin around in circles. This is a simple machine. This is a simple machine that I just designed right here. Who remembers what kind of simple machine this is? It's just a rod that allows those things to spin around in circles. What simple machine is this? Starts with the letter A. Daniel, is your hand up?
No, I'm still thinking.
I see in chat we have axle, wheel and axle. Yeah, it is an axle.
Yeah, I agree.
So let's go ahead. We gave a little demonstration about how we could potentially generate motion using electricity. I'm gonna jump back over to your packet so that we can read about motion, and we gotta mute somebody. All right. All right, we're all gonna read about electric motors. So spend the next 2 minutes reading about electric motors. I put that on the top of the screen right here. I think that might be Daniel. Daniel, you're unmuted.
Huh?
Daniel,
I am?
Yeah, I just muted you. So we're all reading electric motors. Let's see, we got 2 chats going on here. Can I zoom in? Yeah, I can zoom in, absolutely, that makes sense. I can't zoom in that much though. Let's go back to 100%. All right. So we just read about electric motors. An electric motor is basically, I just described one way of creating an electric motor using an electromagnet. By changing the poles of an electromagnet, switching the direction of the current one direction then the next, and that will cause permanent magnets to spin. Either it could spin just like this on an axle, or you could have a bunch of electromagnets that are like in a circle around an electromagnet, and you can make the whole thing spin in circles. There are lots of ways that you can do this. Let's move on to some notes. This isn't letting me draw on my screen. Okay. Some important notes that you should take down are, let's go into the PowerPoint real quick. I think I can probably draw on that. All right, so jot down these notes from the PowerPoint. Electric motors are devices that use current to turn an axle. Give me a thumbs up if you see the screen and you're jotting down the notes from the PowerPoint. Great. Thank you, Morris, for showing the thumbs up. Vicky, are you able to see the PowerPoint? Jotting down notes. It transforms electrical energy into mechanical energy, and it has many uses in appliances. Okay. Yep. We went through this already. The light poles repel. The nail flips. It moves half a turn, causing the axle to move. Let's move on to the next idea, which is generators. So where do you think, Jessica, I see your hand. You're unmuted. Hold on a second. Oh. Go ahead.
Can I read the passage? The generator?
Yeah, you can read the passage. Let's see if this is the same one. Yep, that's the same one you have here. Go ahead.
Generators. An electric generator is a device that transforms mechanical energy into electrical energy. An electric generator is the opposite of an electric motor, which changes electric energy into mechanical energy. An electric motor uses an electric current and a magnetic field to produce motion. An electric generator is made up of an insulated coil of wire and a magnet. The coil of wire is attached to a power source that causes the coil to spin. Spinning the coil of wire in the magnetic field of the magnet exposes the wire to a change in magnetic field. When this happens, electric current is produced in the coil of wire. The mechanical energy used to spin the coil of wire is changed into electrical energy. The ends of a coil of wire can be connected to a load, such as a light bulb. When electricity runs through the wires, the bulb will light.
Thank you, Jessica.
You're welcome.
You can mute yourself, please. Jason. So
Yes.
What is a generator? What do they do? What do we use them for?
A generator is, we use a generator like it transforms mechanical energy to electrical energy.
Yeah, exactly. So what are we generating? Generate means to create.
Yeah.
To make. What are we generating?
We are generating.
What do you think?
Like we're generating electric.
Yeah. We're generating electricity. Let's move on to the next passage so that we can get learn how generators are actually used. And there's actually a really good picture here of how generators are used in power plants. Would someone else like to read the next part of the next passage? All right, Vicky. Yeah, I'm gonna go to Vicky. Go ahead, you're unmuted.
The second one?
Yeah, it's on the screen right now, using generators.
All right, using generators. Most of the electricity you use every day comes from generators. Power plants use large generators to supply electricity to homes, offices, schools, and other buildings. These large generators use very strong magnets and many coils of wire to produce a great amount of energy. Instead of using a crank to supply the mechanical energy, it turns the armature. A turbine is used. The turbine supplies the mechanical energy for these generators. I can read the next one.
Yeah, go ahead.
A turbine is a large wheel that is turned by steam or moving water. It is a large circular device made up of many blades. The water used to turn or spin a turbine may come from a dam or a river. As a result, a magnet spins and generates electric current. Steam is produced, be quiet, Jemima. Steam is produced by burning fuels such as coal or oil, or from the nuclear energy.
Thank you, Vicky.
Mm-hmm.
So using so I'm gonna have us answer a few of these independent practice questions right now. I think that the first two questions are very good review of what we talked about today. How does an electric motor work, and how does an electric generator work? So go ahead and spend the next 2 minutes answering these two questions.
Jason, did you have a question?
No, I was trying to read the thing, but Vicky already read it. So
if you write down these two questions, so I'll go back to the text for generators. So the questions are, how does an electric motor work? And then the other one is, how does an electric generator work? Okay, I'm gonna go, let's share out our answer for how a generator works and then how a motor works, and then we'll close out the lesson. Jalen, I'm unmuting you. I want to hear from you. How would you summarize how an electric motor works? I'm clicking unmute, but it's not unmuting him. Let's go to, all right. Because it is 12:30 now, and I don't want to keep you from reading, I will just review that electric motors work by placing a permanent magnet within the magnetic field of an electromagnet. And if you change the polarity of the electromagnet and switch its polarity back and forth, you can create motion. But you can make this other magnet spin because you keep changing the magnetic field, which is pushing it and pulling it around. A generator works the opposite way. It takes a permanent magnet, which, or even many of them, and it spins them around. And it spins them around a coil of wire. And that spinning causes electricity to flow within the coil of wire. So it's time for reading now. And I would just ask that everybody print out their science packets if you didn't have them printed today. please print out your science packet so that we can all look along, and I can use the screen for other things during the class. Ms. Rahman, it's all yours.